When I was a kid, I was really interested in building things, and I had some of the theoretical knowledge. I knew what kinds of pieces I roughly needed and how they would fit together. I could make diagrams that when you go back and you look at them, they're still accurate diagrams, but there was a lot that I was missing. I didn't know what exactly is the piece that I can buy online, like what's mass produced, or what are the parts called, what are the part numbers, where do I buy these parts, and then how do I take these parts, order them, get them to my house, and then start fitting them together. What are the different techniques that people use, and what kind of design process do people use? Do people figure it all out ahead of time on paper and then order an exact bill of materials, or do they just grab stuff that they have lying around? I had no idea what the process really looked like, and I had this frustration that when I went and I looked at people's tutorials and I watched a video on that or read an article on this or that build, I got a really nice summary of what people had done, but there were always missing pieces, steps that they skipped in their build. And for me, a lot of my questions happened actually in between the footage that they showed. So I really felt like I had to figure out my own path for how I prototype things, how I build things. Um, and I always thought as I was going through all this, and it was the same when I went to university, and even after I was out of university, I was like, oh man, what parts do I buy and how do I put them together exactly? What are people's processes like? And, start to finish, how do they think through different options and choose one? And I always thought, one of these days I have to make some videos that show start to finish with all of the little bits. What is my process like? How do I think through it? And how do I build something and make those design choices? That's what this video is about. In this, I make an LED dimmer for the thing that you see behind me. I got this bookshelf and I had some LEDs on the back and they were way too bright for my TV room, which is where I am right now. So I really wanted to make a little board that could let me turn the brightness up or down. And so I made a really long video that shows all the details of how I made that happen. In the beginning, I'm over at the table and I just have the parts out that are parts from my inventory. And then I just start talking through it, putting parts together, slapping it together. So this video is for people like me, like I was especially 10 years ago, who have a lot of ideas about the things that they want to build and roughly how they want to build them, but not knowing exactly what parts they want to use or exactly the quirks of those parts, how to implement them in a system, or most importantly, exactly the process that they want to follow from design through prototyping through something that I can plug into the wall over there to make whatever their idea is in the real world. I have a few different phases that I go through in this video. At first, you'll see me working on the bench just with my parts out in front of me, kind of putting the parts in place and seeing where I want them to go. Then you see me doing a whole lot of wiring things up and getting the connections in place. And it seems like that's what takes the most amount of time in this whole thing, is just making all of the electrical connections. This hooks up to this, that hooks up to that. You'll also see how I approach the software design. In this, I'm using Claude Code, which is AI, and that should make it easier for anyone who's trying to get into mechatronics work. Is now we have wonderful AI tools that simplify the process, or even if you're already a good developer, it speeds up the process massively. So you can go from your idea to your working thing. So that's kind of a second part of it. Then there's kind of a third part of it, which is the initial benchtop testing where I just have a little LED and I'm trying things out. Then there's another part where I take it over here and I plug it in and it fails and it burns out and one of the pieces almost catches on fire, and I'm really discouraged after the many hours that I spent trying to get it working. Then I shut it all down. The next day I come back to it, sleep on it, I've thought on it, and I return to the camera with some changes that I implemented on the board. Unfortunately, I didn't record me actually building in those changes, but it's nothing really new compared to what you saw in the first couple of hours, or for you it should be 1 hour. I'm just taking more pieces, putting them on the board, using the same techniques, same approach, same process. And then you'll see me plug it in, run a test, and then describe what are the different pieces that I added, the different safeties and good practices that I added to the initial prototype to take it from something that releases the magic smoke in a bad way into something that can plug into the bookcase and has been running for a few weeks now exactly how I wanted it to, with no issues, no excess heat. And then in the last part, I go through the software again because I realize the continuous beginning to end footage, I didn't do a very good job of explaining the software. So at the end of the video, I go through, or at the end of the project, I go through the software bit by bit. I review what is my software workflow like when I want to do a simple little vibe coding project. And it should give you an idea of how you can make that happen using a tool like Claude Code, which I highly recommend. Brief overview of the system. What we're making here is an LED dimmer. You know, I've got this little control board over here. You can use a potentiometer to turn the brightness up and down, and there's a button. Turns off and goes between 1, 2, 3 presets, and off again with the button. And at any time, I can start turning the potentiometer and it will adjust from wherever I am to the next level. So I'm at here, I can turn the potentiometer and it goes down and it goes up from that spot that I'm at. So that's what we're making here. If you have any questions about how it works or how you can make your own or different design alternatives or what different parts you could use, or will it work on this, will it work on that, or if you just want to show what you've done, I'm really interested in seeing what other people's processes are like, and I'm really interested in seeing what kinds of tools and parts other people are using or would like to see used. So please drop a comment, and I'd love to see where your head's at. All right, I just put together some new furniture and I threw a whole bunch of LED strips on it, and turns out they're really bright. It's about 14 amps at 12 volts, and it's in my TV room, and I turn it on and it blinds me. It's like turning on the sun. So I want a dimmer. The problem is you look for a 14 amp dimmer and there are some things that say that they're 14 amp dimmers, but they're not. They're actually filthy, dirty lies. So what we're gonna do is we're gonna make a 14 amp dimmer, because look at this. This is the circuit. You got a MOSFET, you got some GPIO, or something to drive the MOSFET, and there's your LEDs and it turns on and off. Great. So that's what we're gonna do. Now I've simplified it a little bit. I did some math, I figured some stuff out. I grabbed this hunk of aluminum, but I'm just gonna throw a bunch of these parts together and see if we can dim some LEDs. And I got some ideas for how I wanna make it more pleasant than just one of those dumb dimmers you'll find. So let's get right to it. I'm going to use an Arduino Nano to drive the gate of my MOSFET. That's going to let me give it some brains. So let's take it out. Some of the things that I want to do with those brains are, first and foremost, give it a linearization curve. A lot of the time when you use a dimmer on LEDs, you find that most of the knob does nothing, and then one little teeny tiny part of the knob does all of your dimming. So if I make a linearization table, I can correct that. And if I do that, you'll see how that works. First, let's just get this guy mounted up.
We have some stumpies in here. Let's get some stumpies. Let's get a solder in.
That seems a little hot. Let's take it to 293, maybe. And see how we feel about that. Shouldn't need these for a little while. Let's just throw that down on the ground. All right, it looks good. It's starting to act a little gummy and sticky, so I'm gonna just wipe it off. you kind of see me do a little bit of a 1-2, because the 1, oh, I just bridged. The 1 is me wetting the iron with, I bridged again, with fresh solder, and the 2 is me moving the solder to the opposite side of the pin to let it flow through. All right, that's all soldered up.
Inspect all those joins.
I'm happy with everything I see. There are no shorts. Okay, now I think I would like to make this a debuggable circuit. So I'm going to put female pin headers so I can plug and unplug this guy. Let's see, if I do that, this here, MOSFET, this will still comfortably fit, right? I'll get to talking about this later. This can fit something like that. Maybe I'll even hang it off the edge so it can blow a fan through these fins. Nice. Because what my numbers show me is that this MOSFET, this IRL-Z44N, is kind of an old MOSFET, but it works turning the lights on and off with the 5-volt gate drive that I get out of this microcontroller. But the RDS on is the resistance that this offers when it's acting as a closed switch, and that's 28 milliohms on this device, and that means that when I'm running 14 amps of LEDs, I'm going to be dropping 5.5 watts over this guy. So without a heat sink, it has a junction to ambient resistance of 62 degrees Celsius per watt. That would put me at 340 degrees Celsius over ambient, which is pretty garbage. So with the heat sink, it should drop that. One annoying thing about the heatsink is this whole aluminum blob is going to end up getting energized, so I'm going to need an enclosure around this. But with the heatsink, it should take that 62 degrees per watt and drop it to like hopefully less than 10. So then I'll be getting maybe a 50 degree rise at full on, but then with switching losses, maybe it'll become hopefully less than 100 degree rise. So hopefully this will be running at less than 120 degrees Celsius without a fan. But then I'm going to blow a fan right over top of it. So hopefully I'll have this running at ideally maybe 80-ish degrees Celsius. Fingers crossed. We'll see what we get. I do just want to check and make sure this fan is working. It says 5 volts on it. And I don't really want to run it off this guy's 5 volts, but I do have my power supply that I'm using for my 14 amps of LEDs is a computer power supply, an ATX power supply. And that comes with a 5-volt rail, because computers like 5-volt rail. So I have 5 volts.
Let's see if this fan works.
Just go in the spot so I can feel how tough this is. That's pretty good. Yeah, it's a little bit loud, but I think it'll do a good old job. Because I'm going to have to put this in a case since that stupid thing is going to be energized at 12 volts with a bajillion amps potentially. Okay, good, the fan works.
Oh no. Oh good, it didn't burn. Be careful with your soldering iron, guys, I say as I touch it to plastic. Goodness gracious. Alright, step 2.
Female headers. I don't see much in the way of stubs. Ah, here we go. I got a short one here. Is that going to be enough for 2? 1, 2. It's not enough for 2. Oh well. Let's do one piece at a time. All right. Let's put that right about there. Let's see, I'm going to use one analog pin for the potentiometer. I'm going to use this guy. It has this nice thing where it clicks off on one side, and I really like that. Perfect for an LED dimmer. But I'm going to have an analog signal here. That's going to be this one. This is the pot circuit that I'm going to use. And I'm actually going to use a different board for the controls. I'll have the button maybe here, and I'll end up mounting the potentiometer directly to the board. It'll live somewhere down here. And the button is going to let me switch between presets, and then the knob is going to be like when I decide I want something that's not one of the presets. Okay, let's start up this next bit. Let's hold it like that, nice and gentle, just enough to stay put. Turn that on. Get to solder in, solder in, solder in, solder in. Burn some. I just did those opposite points like that to anchor it. So it's probably a little bit difficult to see exactly what I'm doing here, but I put the solder past the pin, close to the iron. Then when the iron comes in, it touches the solder first, so that wets that solder to the iron, so it gets this nice puddle on it, makes it real thermally conductive. And then I push the iron with its puddle against the pin, and then the solder's melted back, and I apply the solder to the opposite side of the pin. And that's my 1-2 step in one. Inspection. This one looks a little janky. Some of them I didn't put quite enough solder to bring me joy, so I'm just adding a little bit more to bring me joy. Enough. Okay, now should probably mount the MOSFET. That seems like the most important part of the job. Do I want to do that? Yes, I do, because then I'll route power and all that goodness. So let's get this fastened on. That looks like an M2 maybe. Let's go get some screws. Of course it's not an M2. Why would it be an M2? I don't stock M2s. Probably an M3. I love keeping things in boxes and bags like this. It's a super pleasant way to keep things organized. My favorite way that I've ever seen anyone use. I've done it like that for years and I love it.
Okay, oh, where'd I put my screwdriver?
Yeah, that fits good enough. So if I had like a insulating thermal pad here, that would be great. Might be able to stop this whole aluminum heatsink from turning into a 12 volt, I don't know, 25 amp fire hazard. But unfortunately, I don't have a thermal pad. I don't even have thermal paste. I'm just putting it on there dry. It'll still remove a lot of heat, especially with that fan, but I'm going to have to 3D print an enclosure to stop it from shorting against something and breaking everything. Let's get this soldered in, and then I'll probably put on my power wires next. And I think I'm going to do all of the connections off this board with just spade connectors, because who doesn't love spade connectors? Everybody loves spade. Oh, putting a heatsink on is going to make the drain really hard to solder. The drain is in the middle. Maybe what I'll do is just see how lucky I am.
Yeah, that sounds smart. Just see how lucky I am. Because that works literally every time, right?
I'm saying because I'm going to hold this in a nice position that's going to make the soldering pleasant. Okay. I'm going to do these outside ones first because the middle pin is the drain, and the drain is electrically connected to the heat source, or the heat sink, so soldering that's going to suck, probably. Make sure that our iron is up to temperature. Okay.
Now let's see if we get lucky.
Oh, we got lucky. That was actually incredibly easy. Great. I guess there's enough of a gap there to those pins. Wonderful. You can go back in your house. Thank you for your service. Okay.
Let's get down to business to defeat the Huns.
I turned that off. No, I did not turn that off. Ooh, let's do that. Go off. What is this? Oh, yeah, I don't need that, right? That's why I put it on a thing. Okay, great. So now this circuit, I should choose the GPIO that I want to use. I need to use a GPIO pin that's going to be PWM enabled. Let's see. Can I turn on my screen recorder? Does this work? Hey, yeah, that works. Arduino Nano pin note. That's good. Pretty clear. Do all the digital pins PWM? Well, this is TX-RX, so I don't want to use that. I don't really need timer interrupts. Let's use D2 and D3. Arduino Nano PWM capable pins. Oh, why isn't this on the diagram if it's... Oh, is that this wiggly? The wiggly is PWM. That's what it means, isn't it? Maybe. Let's see, 3, 5, 6, 9, 10, 11, 12. 3, 5, 6, 9, 10, 11. Oh, not 12. Yeah, this wiggly is PWM. Okay, let's do 5 and 6 then. Because if I can use 2 of them, that would be nice. Maybe well, one of them should do it. Let's see, Arduino Nano GPIO current. 20 milliamps per pin, while the absolute maximum is 40 per pin, exceeding 20 grade. Okay, so if at all possible, I would like to run 2 of these in parallel. Let's just double check with the AI. Arduino Nano PWM. I want to use D4 and D5 in parallel to gate drive with more current. Gucci? Yeah, that's fine, but you must be careful to avoid destroying them. Things to be careful about, use independent gate resistors. Okay, just in case. Synchronize the code, write the pins using direct port manipulation. Okay. Keep resistors above 130 ohms. What do I have in my resistors? I have 180. Well, what's 5 over 180? That would give me 27 milliamps. Yeah, that's fine. Okay, I'll use 180 ohm gate resistors. That's this resistor right here. I thought I turned this off. So I'm going to use a different gate resistor on each of those two pins, and then those two pins together are going to connect to the gate of the MOSFET, which is this one on the left. All right, D4 and D5. But can I not do that with the PWM peripheral? I don't want to manually loop that. Yes, you can use the hardware peripheral, but not with 4 and 5. Oh, D4 is not. Oh, gee, I meant 5 and 6. Okay, yeah, 5 and 6 are the pins, not 4 and 5. I don't know why. It clearly has in the diagram 5 and 6. Okay. And about port C, I think. Is that right? Or is that just output control? I don't know. I configure match pins, force 2 pins. Configure the times control registers to operate. Both compare match channels. Non-inverting customer one. Rest of the exact same. 3 cycle value. So the transition at the same time. Okay, I'll get to that later. So yes, it can be done. I'm going to put 180 ohms on each. So that way, even if they start going in opposite directions, they will not go over their capability limits. Because that would be 5 volts divided by 360 is only 14 milliamps. Great, on 5 and 6. So how do I want to route this wiring? Let's just put, how do I want to do this exactly? Oh, I'm going to have to put a resistor under the board. No, I don't want to do that. That's nasty, nasty bad. I'm going to put it like this. Yeah, that's decent. I can live with that, at least, without it killing me. Okay. Please don't be that ugly. You're on camera. Maybe I should be less fat. So let's go right here. Ish. This will be exactly what I asked for. All right. Let's get those soldered up. Solder up. Pooey. Pooey Louie. Maybe I should be doing the power wires before I do the gate wires. It's too late now. Is it? Let's see. We need the drain to connect to positive. It's not really going to be positive because it's going to be the negative side of the LEDs, but the other side is more negative. And I'm going to call it positive because it's this guy's positive. Okay, the drain is in the middle and the source is on this side right here. So I can have my negative wire coming out like that. Then the drain is going to be like that. So I think I'll actually have my positive wire connect like here. That'll be interesting. Okay, so then I really don't have much to worry about because the gate can just come up this way and it'll just be a happy camper. The drain is connected to the heatsink. The source is over here. What I actually really want to be careful about is I made this heatsink touch those metal pads. So maybe I want to have the source come out this way, just so it's super impossible for the negative wire to touch this pad, which is touching now this heatsink through the via. Maybe I should even drill out those vias just so it's impossible to short circuit that. I could put it on my to-do list or I could do it right the heck now. So let's just do that. Let me connect it short. This way. Let's see this one. Oops. A little further. Okay, so that's the things like that as well. Got it. What I'll do is the drain's going to go this way, the gate's going to go this way, and the source is going to live over here. Yeah, that'll be safe. Okay, let's do the gate first because I feel like it. So the gate is this guy, which means it's this guy. So just to avoid those fins, I'm going to come out and then over. Let's see if I can do this without dropping the temperature of the iron a little bit. Who needs PCBs? gate is connected. I might as well prep these. So I'm going to have sources on each side. The source is going to be connected to the 0 volts, and the drain is going to be connected to the 12 volts. Okay, where's the wire I want to use for the power? Here it is. This speaker wire. It'll do what I want. I want it to carry 12 volts, which is within its insulation class, and I want it to carry 14 amps. And yeah, it looks thick enough. And let's take it like that now. Okay, drain in the middle. Drain is the one that's not connected to the rail. I'll put it in its spot. This temperature is a little bit too low for this size wire. Just turning it up. Okay. That looks good, clean, solid. Except that I did it with the black wire, which is just the exact opposite of what I wanted. Why do you do this to yourself? All you had to do was be not dumb. It's okay. Solder is a forgiving sculpture, as long as you don't do what I just did and be dumb. I've got a few little stray wires wandering here, and I can't have that. No, I'm actually a little bit suspicious that I might have created a short. Let's just bring out the multimeter and do a check. All right, more than 1 mega ohm, and that might just be my thumbs even. 0 mega ohm. Okay, yep. We do not have a short. Okay, no, this circuit is wired. I want to put spades on here, but let's do the rest of the board wiring first. So, the LED power, do I not actually have 12 volts connecting in here? I don't. Yeah, this is just a passive power. So let's give it some logic rail power.
Isengard. Do your job. Ow. 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 Be careful when you're cleaning your soldering iron, because sometimes it makes little beads that love you and want to live on your skin while they are in liquid metal form. And I can attest from my experience 30 seconds ago that it is not a comfortable feeling.
By tacking them both in, now one holds the other while it's wet. It's easy. The Arduino now has power coming into the board. I'm going to use the 12-volt rail from my ATX power supply for that. What I'm going to do is this board is going to connect to 2 different plugs. I'm going to have one plug for the power supply and one plug for the control board remote thing. And the control board remote thing is going to need 1, 2, 3, 4 pins, I think. I'm just trying to decide what kind of connectors I want to use. Because the power supply is only going to need 3 pins, and they both should probably have their own connectors. Yeah. So, how am I going to do that though? I'll use D12 for no, I'll keep them on this side. So on this side of the board, I have my 5-volt rail, and I can use A0 and A1 and A2, and I can use A2 as my ground pin, maybe, which is kind of weird. Wow, it's kind of weird. No, I don't want to do that, because if I do that, it'll throw off. When I push the button, it'll change my knob. ADC, probably. I could just do A0, A2, A3, and A... I'll just use 4 of the analog GPIOs, then. You get your own high and low, and you get your own high and low, and then I'll also send 5. So if I just do that, then that makes it very easy. That's my control board plug. Just that. And then my power plug can live... Well, this is going to plug into power. This is my power plug. You just have a big deal. So I'll do the same thing for 5 volts. And that'll be fan. And we don't care about anything else. That's all I care about. Yeah, I like that. Okay. Keep it simple, stupid. Mission complete. So we have our off-board connector. So does this actually run now, theoretically? I plug in my 12 volts, and I plug in my things. Yeah, let's just check and make sure that we're not insane.
Because we're probably at least a little bit crazy.
Let's put a simple 50% PWM code in here right now, and see if it explodes my lights. Come on, lights. It needs to be. Okay, let's check this again. We have our gate, and then our drain, and then our source. Our source on a low side end FET is going to be 0 volts, and our drain is going to be our positive rail. That's why the black one is on the source, which is on the far side, which matches our pretty picture, source, dark, 0. Good. Not backwards at all. Let's see, this counts as a power provider, or, well, wait a minute. The negative end is actually going to be plugging into a power provider, but the positive end is actually going to be acting like a power deliverer. So this is weird, because normally I give a female for power, I give a female to a power source, and I give a male to a power drain. In this case, the source is going to drain, and the drain is going to source. Because this negative is going to have to plug in to my power supply, so it's going to need a male spade. Meanwhile, my LED strip is going to plug in to here, because this is now going to be the thing that sinks it. Right, now let's get this connection. Where's my solder? Do you see my solder? Did you take my solder?
What the heck?
Ah, there's one.
You cannot take my solder from me. Beer. Do I have beer? I should see if I have beer. I love beer. I don't think I do, though. It's always worth checking right after you make another solder joint. Try to be less dumb. Do it right and not wrong. Okay. You see how that was less stupid? Proceed with less stupid methods of doing things. Please and thank you for your advice. Pro tip, if you blow on things, they will cool faster if they're hot.
Can help the solder solidify faster.
So that you don't have to be not stupid for as long. And you can more readily return to your regular stupid programming.
Power plug. Okay, this will be my 12 volt power. Now I just need a load to test. Do I have an LED here? Give me an LED. You don't have LEDs? Ah, you have LEDs. LED, green. Green is a good type color. This wants 1 to 20 milliamps-ish.
Okay.
And the voltage drop is 2.3 to 2.7-ish. So if I, let's just make it a full 20 milliamp brightness. So that'll be a 2.7 volt drop.
12 minus 2.7 is 9.3.
And that's going to be 20 milliamps, so 9.3 volts divided by 0.02, because that's 20 milliamps, is 465 ohms.
So what do we have here? 643.94, no, 510 is what I have.
That should be pretty bright still at 510. I have 470.
I'm doing that. I'm doing the 470.
With LEDs, I really like to write down the spec like this, because there's a whole range of currents I can work on, and depending on the current you run it at, the voltage drop changes. So if I want to run it at full brightness, then it's going to have a 2.7 volt drop, so I need the resistor that will give me 12 volts minus 2.7 divided by 20 milliamps. So that's why I do that. But if I want to run it at 1 milliamp, then I'm dealing with a 2.3 volt drop instead. And on this one, 2.3 to 2.7, that's not a massive swing, but on other ones, it's really big and annoying swing.
Long one is positive. Long one to the little thingy is positive. Okay, great.
Always remember to engage your safety squints. All right, now we're going to test this by going like that and that. And seeing how bright it is. Maybe I'll set the PWM to like 15% duty cycle, so it's pretty clear if it's dim. Okay, programming time. Now to clarify, I said programming time, but what I meant was actually make Claude do all the work time. Even though this could be a super simple program, I decided that I wanted to try and use 2 GPIO pins in parallel, so that's going to require some direct pin manipulation, or register manipulation to do that safely and smartly. And I don't like to read data sheets because that annoys me and takes longer than 5 minutes. And this is a 5-minute project. So instead of being smart, I'm going to make the computer be smart for me. All right. VS Code. Now, let's just not remember how to do anything that we do.
C code.
Folder. LED dimmer. Okay. PowerShell. Terminal. Great. Let's just do git init. Initiate git add dot. Let's just make ourselves a readme file. readme.md. Great. LED dimmer. We have an Arduino Nano with pins 5 and 6 connected to the gate of a MOSFET. And we want to use that MOSFET to dim a string of LEDs. Pins 5 and 6 are connected to independent gate driver resistors. We want them working in parallel to PWM, the MOSFET, at 20 kilohertz, so that we can't hear anything, because 20 kilohertz is a higher frequency than we can probably hear. Okay, we want to use direct register manipulation to make sure that pins 5 and 6 are synchronized in their PWM shindig. Quick test. We want to run a quick test with a stupid, simple program that puts us at a duty cycle of 15%. End goal. We want to use a potentiometer to control PWM duty through a linearization table that we will estimate initially estimate to roughly follow a log scale, then tweak later. We will start with 5 points in the linearization table, 2 boundaries, and 3 in the middle. We also want a button to switch us between off preset 1 and preset 2. When we detect a change in the analog pot, we ignore the button and switch to analog mode. Count in function. We have D5, D6, gate control. Then we have A0, A1, A2, A3. This will be always low. Button signal, always low. Button signal. That's all we need. Okay, this is enough, I think, maybe, to tell Claude what we're doing. Then let's just do a claude.md. I want this project to be fast and simple. You are making me a platform.io program for my LED dimmer controller running an Arduino Nano. Okay, this is pretty rudimentary, but I think it might do the job.
Cloud, do the thing.
So because I started Claude in this folder, it automatically read claude.md, and it should be smart enough to read the readme.md. Yeah, there it is, it's reading the readme.md. So now it should just go. I'm just gonna let it go. It shouldn't actually need any additional information from me right now, I think. It's a decent enough programmer. It should understand what I said. Let's see, I'm getting some water, and it might be done before I even sit down, and that's why we use AI. Oh, it's not done yet? I told it to use direct register manipulation. I told it we're using a Nano, I gave it the pinout. I told it to do basic mode first. I might as well get the power supply ready at 12 volts. Let's just turn down the current limiter so I don't dump a million amps into it. I'm setting it at 2 amps, which this LED can't take 2 amps, but the MOSFET can.
2 whole minutes?
I don't know, it's been a while since I asked Claude to do something embedded. Maybe it's just not. I think it's not as good at embedded code. It's great at like web code. I can tell it to make me like a dashboard and it just does it. It's like lightning. Embedded is a little slower though.
And a little dumber.
So let's just see what 12 volts looks like. Let's see if this LED burns out. I didn't do it backwards, did I? Oh, I'm 100% plugging it in backwards right now. Yeah, it's pretty bright. That's super bright. Oh, geez, it's freaking hot. I didn't check how much power that puts through that resistor. What the heck? I used a 470 ohm resistor and 28 milliamps. 0.02 squared times 470. Oh, this is a quarter watt resistor, and I'm putting 0.2 watts in it. It's using 75% of its total capacity before burnout. Yeah, that resistor's gonna get hot. I should have thought about that. But at 15% power, it's only gonna use 11%. Oh, come on, Claude. Come on, Claude. This is basic. Oh, come on, Gemini had it in seconds. What are you doing? Well, I didn't tell Gemini to configure a platform environment. But come on, you've done this before. You can do this.
Right. Right.
Oh, man. 5 minutes.
I'm getting a snack.
Shouldn't I be using these 5 minutes to prepare the next step for success?
Yeah, I really should, actually.
I should be using these 5 minutes to prepare the next step for success. Let's do that. Let's prepare our remote control board. We haven't done that yet. It's gotta happen.
It's gonna happen today. So let's do it.
Let's do the button.
Where even is this thing connecting? Oh, there it is.
Okay, button's done. Now let's do the button.
Everybody loves pot. Everybody loves pot. I forgot to check if I have beer.
Probably don't. I might have whiskey.
I got a little bit of yummy whiskey. I got a little bit of not so yummy whiskey too. What's the point of that?
Oh.
That was a little bit more aggressive than I originally intended.
And these things, I want to do something like this. So I think I'll drill a hole. And I'll drill a hole that way too. Okay.
What kind of hole do I need, dear Lila, dear Lila? Or Liza. It's Liza, not Lila.
I'll start with this because it's a superior build it, and then I'll switch over to Chico build it. So I'll start. We can start on the edge.
I'm on the edge, going. Oh, I'm like a fish. A fish. Right approximately about kind of there-ish. That's not where I started that hole. Did I melt some shit on the end? Okay, this is what happens when you're not actually doing anything. That's interesting. I think I need to push harder, and that means that I should actually use what I said I should use. Wood. And what do you know? Instantly done.
Yeah, but because I tried to do it the dumb way, my hole moved. So let's see if it fits anyway.
Fits enough. fits enough.
Okay. Now, let's solder it, because we can.
Wait a minute. Did Claude do the thing?
Oh my goodness, I did not put it in dangerously skip. Allow all edits. Thank you. I usually just run it in dangerously skip permissions so that when I stop paying attention, I come back and it's all done. And as long as you set up your docs right, it usually doesn't do something supremely moronic. Usually. I've never borked my system with dangerously skip permissions.
Mechanically secured.
Excellent. Now, after drilling a hole, I get that bit right out of there, because if that drill falls over, it's going to snap that cantilever right off. Might as well put it in its spot. Sturdy enough. Good, good, good. It's a little crooked, and this is how much I care.
So much that I go into the other room to cry for a little bit. And return with my wire. Ouch.
Okay, what does Claude say? Claude says, done. 2 files created. Platform I/O targets the Nano Atomago with Arduino framework. Main CPP, full implementation. Key decisions worth knowing. PWM frequency, 62.5 kilohertz. Didn't I tell you specifically? 62.5 kilohertz is not what I want. So this is a problem. That's going to increase our switching losses too much, and we're going to generate too much heat.
Let's let it chew on that for a bit.
It wants me to rewire to pins 9 and 10 because it's a 16-bit timer instead of an 8-bit timer. What happens if I run at 31 kilohertz?
31,000. That is 32 microseconds. That's 6.8% times, call it 70.
That's 5 watts of power compared to 4 watts. It's like another 20.
It could be like 10-20% more heat. I'm putting a fan on it.
Let's see, what if I do switch to 9 and 10?
It's actually pretty easy for me to do that.
Okay, switch 2 pins 9 and 10 to get us our 20 kilohertz. All right, 9 and 10, those are 2 from the end. All right, 9 and 10. Another advantage of Claude is Claude just does that while I'm working on the solder.
And then it's just done before me. And that's 9 and 10. Good.
Good. Exactly 20 kilohertz. Okay. Give me a build script while you're at it. Why not? Oh, and it already implemented the whole damn program, including the analog setup. So I should really...
Did it put a pull-up resistor or something? You put an internal pull-up on the button. Okay.
So that simplifies my button circuit. Yep.
I can't actually run my test until I get this board ready now.
Okay. Well, what's it saying about a build script? should probe these guys to see exactly how they work.
Okay, that's how you work.
This is only 1 kilo ohm. That means it's going to take 5 milliamps. Alright, seems like a lot.
That's interesting. So we actually, this down here is a power switch. I'll implement that later. First up, the button. Because I can actually do it all with the button.
What did it set the presets at? $25 and $75.
That's not what I asked for.
What is that?
200 divided by 25 times 100. 800-ish. So what's 800-ish times 0.15 is 120. Let's do that, please. And that.
Okay.
I want snacks. Oh, I forgot dinner. That's why I want snacks. Not enough goo. Give me more goo. Never forget to engage your safety squints.
Okay. Where did we put things? We put button between A2 and A3.
What? Shit.
I actually put the wrong things in this document. Let's see. I didn't put it as a constant or anything. I'm gonna make Claude do this because it's using direct pins and it didn't do like macros for an easy change. So let's put the button on A4 and A5. Let's do 7654. Okay, the button now goes here, and I should be able to run the whole program with the button. Maybe I should have given the LED some better wires. Where did I put the LED?
How am I losing stuff all the time? There it is. No. I think I'll give the LED the same treatment. Do you think?
Okay.
Do I have to say PS first? Is that what it is? I feel like that's what it is. I'm pretty sure. No. What is it? I don't use PowerShell. Oh. Well, that's boring. Can't just figure that out. Great. Uploaded. Let's just see if anything explodes when I plug it into 12 volts. I'm going to keep an eye on the current limiter.
If I was smart, I would check for, wait a minute. Yeah, I did bridge those.
Try not to plug it in backwards and explode your board.
Move the solder out of the way so it doesn't short circuit everything. Okay, we have the 12 volts.
Oh.
I need to make a fork on the 12 volts. That plugs into this. Oh, I'm still not ready.
How much of a frickin' test circuit do we need?
Well, how do I want to simplify this? Because I want a nice, clean interface. Maybe I'll get another board to be a distribution board. I'll just throw it in the enclosure.
Oh no. I made a mistake. There's one. Two. I feel like it's easier to see the pathway this way too. Nice and easy to understand. Or at least it will be when the pathways are made. I don't know if it's clear to an observer yet. I can kind of see already where the pathway is going to be. I don't know if that's obvious yet. Should be soon, if it's not already. Input power, LED power, dimmer power. That's what's going on. Finally. Alright, I got my distribution board. Can live right next to this one. Right over here, perhaps.
Maybe over here.
I don't know. I'll figure it out.
Oh, but I also need the ability to plug this thing in. the 12 volt power. It's got to plug into this board. The spot right there.
Okay. And now your turn. Ah, poo. Pooey Louie. Goodness gracious. This is not as simple as I wanted it to be.
Okay, so resistor 1 is positive. This is full brightness, and it's pretty freaking bright. Now we're gonna find out if I just wasted a whole bunch of time. Yep, a whole bunch of time. It actually looks really dim. Did I just burn out the transistor?
I think I broke something. Why is it broken?
I think I burned out the resistor. Why? Isn't it 470 ohms? I definitely burned out the resistor. What?
Oh shit.
I forgot to connect the power to the Arduino.
Man, and I burned my thingy. It hurts.
You didn't just do that with the power connected, right?
Yeah, you did. You did. You did that. Okay. You did that.
Then why isn't it powered? It's amazing how hot a resistor gets. You think it wouldn't get as hot as a soldering iron, but gotta remember, a soldering iron just is a resistor.
How many times are you going to solder on a board while it's live? Why do you not learn your lesson?
Okay, now you have power.
Real power. True power.
So let's get this guy a bigger resistor.
Because apparently 478 not enough. V squared over R.
I need at least 5. I don't know why I decided before that it was okay to do 470. And I still can't touch the damn thing. It's gonna get toasty. It should survive.
All this to damn a frickin' light bulb.
Full brightness. Oh, I didn't burn out the resistor, I burned out the LED.
I'm just gonna blob this shit up.
Okay, full brightness, hopefully. Very bright, good. Well, it's definitely dim, but it's unstable. Oh, I know why it's unstable. Because it's still reading changes in the analog. I actually need to wire this up. This potentiometer can no longer be ignored.
Pooh. Rage, rage, rage.
So I don't know if I said this out loud, but the reason why the LED was flickering is because without having this potentiometer plugged in, the analog input pin that's supposed to be connected to the center tap of the potentiometer keeps on moving around. And we made a rule in the program that whenever the position of the potentiometer moves, it overrides the preset and switches into analog mode. And so the brightness starts being controlled by the potentiometer. So even when we hit the button, the potentiometer immediately drifts because it's a floating point, and then it goes back into analog mode. It effectively ignores the button. So what we need to do to fix that is connect a 3-pronged plug here to this potentiometer. Now I'm going to need a cable that has 3 things. I wish I had some spare RJ45 lying around. Would do the trick. For now, I guess I'll use this.
I don't mind just a little bit of liquid solder in your face. Everyone loves liquid solder in their face. Oh.
A6 is ADC only on the Nano. It's not capable of driving low. I need to physically tie it to ground. Okay. Always another something.
Weird. Wish I knew that before I did this. Also, just noticing that the buttons in the pot were never connected to their GPIO. So that's great.
Oh, this is great. It actually works perfectly.
Oh wow, you're still recording. Okay, nice. Is this still recording too?
No. Guys, I'm really happy about this right now. I'm going to turn off the screen. All right, so we finally have the working prototype. This LED apparently doesn't want to turn off all the way, so I might need to investigate getting a better shutoff. However, we have our 12-volt power coming in. This line over here goes to the LEDs. This line over here goes to the dimmer. And then we have our control board, and we have a button with our presets. And then we also have our analog knob. And we have whatever we touch last is what controls the light. So I can switch through my presets, or I can move the analog knob, and either one of those will take over. There is a minimum brightness though, so I'm going to have to see about that. Apparently it doesn't turn off quite all the way. I'll figure that out. Oh, this is an AVR quirk. It doesn't do 0% duty cycle. So Claude just did a clever trick, and it's already got the linearization table in there. Good job, Claude. It's done a really great job. And now, off is truly off. Okay, I'm gonna try it on the real deal. We're gonna see. I don't know if it's gonna explode. Let's find out. By explode, I mean overheat. It might overheat bad. Okay, let's see. Let's see if everything goes to shit. Oh, it's this one. Turn off the power. Now, moment of truth. Will it break? Yes. Yes, it broke. I'm gonna try again.
Oh. Okay. Well, something definitely caught fire. Not sure why.
Yeah, not sure why. But if the potentiometer caught fire,
Which it did.
that should not be physically possible unless the Arduino caught fire.
Which is sad.
Okay, yeah, it caught fire. We caught fire, guys. We're on fire. No, it makes noises. Bad noises. It makes bad noises, guys.
That's sad.
What happened? The load is bigger, but it's not so big that it should have created a different thing. Yellow is positive, black is negative. I don't know what happened. The potentiometer is supposed to go through the 5-volt regulator. The pot only gets power after passing through the 5-volt regulator. V squared over R. 5 volts times 5 is 25. R is 1,000. 25 milliwatts. This should be fine at 25 milliwatts. Well, guys, I'm kind of discouraged. I'm gonna have to sleep on it, but probably this pot is dead. Likely this Arduino is dead. I'd be surprised if the MOSFET was dead, but based on what we just saw there,
Let's just take a look.
I can't tell just by looking at it, but probably the 5-volt regulator on this Nano is fried. And who knows what else.
I mean, if the pot was on fire, then probably every other chip on the board was on fire.
I don't know if this was caused by a surge or what, but I'll need to think about it. I'll need to figure out why. Oh, that's not what I wanted. All right, so I went back to the drawing board and I made a few changes to the thing to make it so that it will hopefully not explode when I plug it into the 15 amp circuit. So one of the big things I did is I added flyback, this So there might be a little bit of inductance because I'm running 20 meters of LEDs and it's 14 amps maybe. So put in a flyback diode using another one of those transistors, same transistor that I used for the switching, just using the internal package diode from that. Threw some caps on it.
Some 0.1 ceramics, 0.1 micro, 1 micro ceramic, a couple of 100 micro electrolytics.
And some other stuff, and improved the grounding. So now I'm going to plug it in, give it a try. All right, we're wired in. Gonna give it power. The power light's on the Arduino. Nothing's on fire. Look at that, that's a good sign. Our 5 volts is good. Now if I click on this preset button, we should see the first low light level preset on the LEDs. Ha 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 ha! Ooh, ooh! And there's 100%. Oh, that's lovely. Oh, okay. Now if I turn the pot, it should adjust from. Yeah. And now we get some nice adjustments on the potentiometer. Oh, yeah. Another click should turn it off. On. 1, 2, 3. And we can adjust. Oh my goodness, that feels so good. All right, I want to show you what's going on inside this box. Okay, so now you can see the different moving pieces that we have in here. I'm just gonna turn everything off and unplug it and wire it back in so you can see piece by piece what's going on. So first I turn off the power supply with this little jumper, and let's get it all unplugged. Okay, so first off, the power supply. This is a standard desktop computer power supply. It's called an ATX supply, and I've cut a whole bunch of the wires and put this board on here, which is just a proto board where nothing's going on. It's just a few places for me to connect wires conveniently. So there are no components on here except for jumpers that I can put in to do stuff. Now, the way an ATX power supply works is there's this green wire here, and that's the on-off power wire. And the way you turn on the supply is you short that green wire with a black wire, and then that gives the instruction to turn on. So just to make that easier, I have this little jumper over here, and these 2 pins turn the power supply on. So you can see the power light at the back. When I put this in, the power light turns on. When I take it out, the light turns off. So that's the first piece of this puzzle. And these power supplies are wonderful because they give you a 12 volt rail, at least one, a 5 volt rail, a 3 volt rail, and a minus 12 volt rail. And it's awesome. The 12 volt rail on this gives me 17 amps of power. The 5 volt rail gives me 16 amps of power. And you can find these all over the place because old computers still have good computer power supplies. And they're just so wonderful, perfect for LED lighting. Now, this is just the power wire to the LEDs. And from the board, the 12 volt lines are in yellow, 0 volt in black. And over here, I have some headers for the 5 volt line, which is red. So now, to plug in our system, first we have the distribution board. This used to just be simple distribution, but I've added some components on here, and I'll talk about those later. But we have our input power wire that we plug into the ATX power supply to get our 12 volts. Then this is our delivery wire that we send to our LED strip. And this here is our control side where we can switch on and off the LED wire. So that's where we plug in this, our PWM board, that controls the main switching MOSFET that does all the work. Then this is connected to yet another board, and this is our remote control board. So here we have our button that flips between presets and our knob to do fine adjustments. The only knob that I had on hand after I burned out that last knob are these 10-turn potentiometers, which I really like. but I didn't originally want them for this project because you don't want to do 10 turns to get just the brightness level you want. I ended up implementing a trick in the software to get around the inconvenience of using a 10-turn pot for this job, and I'll tell you about that later. Let's get it plugged in. So first, I'll plug in the load. Oh, that's the LED strip itself. And you got to make sure you get your polarity right. I have a black wire and a clear wire. Black is negative. Then we have the switching side plugged in, and the switching side is plugged into the remote control with these right here. The next thing to plug in is this here. Instead of taking power from the 12-volt line and going into VN, one of the upgrades that I made to make this more robust and less prone to exploding is taking this 5-volt rail for the Nano and plugging it directly in to the ATX power supply's 5-volt rail, which is more stable, regulated, and isolated from the 12-volt line that has all of our noise on it from the switching. So that's that. And now we can plug in our main power source. I like to do COM first, ground first, and 12 next. Now everything's plugged in, all we have to do is switch the power supply on. So we'll do that with this jumper right here, moving it over. And now it's on. Now we have to be really careful with these heat sinks. These heat sinks are actually live voltage. This one is at 12 volts and this one is switching. So this is kind of a crazy voltage on here. But now you see the light on the Nano and we can run our test. And I think you can see a little bit of glow from the cabinet. It's very obvious to me. And we can adjust up and down with this potentiometer now. All right. Now is the part of the video where I show you the changes that were made and why it took it from explodey to not explodey and what each thing is for and why it matters. So the first change is I took the power rail and I switched it to provide the power to the microcontroller. I switched it from the 12-volt line to the 5-volt line. Now you have different ways that you can power an Arduino board. One way, probably that most people use, is with the USB port. Probably the second most common way is by using the V-in pin. That's what I was using before, is you can provide a voltage to the V-in pin, and then that voltage will go through this voltage regulator and 5 volts will come out of that and go to the microcontroller and go to the 5-volt pin. Now, what happened is on this board broke down because something happened that this regulator couldn't handle on the V-in line or on the ground line or on both lines, and it resulted in this frying and short-circuiting. And what that did is it sent 12 volts to the microcontroller and 12 volts to a bunch of other things that were supposed to be running on only 5 volts. And this cooked and things were glowing and it was smoking and it was bad. So the first change that I did is I switched to, instead of using VN, just using a whole separate power rail and plugging this into that nice clean 5-volt rail that we already get for free from the ATX power supply. That's one big change. The second big change I did is I added a trace on the board between the microcontroller's ground and the ground as seen from the MOSFET. Now, theoretically, I already had that before, but it was going through this wire to the distribution board, and then the distribution board had this other black wire coming to the MOSFET. And that loop, with the fact that there's power going through this cable here, it just made the possibility for the 0 volts here to drift from the 0 volts here, so that the control signals going to and from the MOSFET were not quite at the level that they should have been. I don't know if this was happening or not, but to ensure that it was behaving properly, what I did is I added in a solder trace to directly tie this 0 volts to this 0 volts to make it just more robust that way. Another change that I did is I added a resistor right here, and this connects the gate of the MOSFET to 0 volts with a 10K. Now 10K is a big enough resistance that it's not going to really do anything when the system is running. Like we control this MOSFET with a 100 ohm gate resistor, but and that 100 ohm gate resistor is going to dominate in the normal case. But when when the Arduino turns off, the GPIO is technically floating at that point. So if the 12 volts is energized for some reason while the Arduino is unplugged or not responding, you can end up in a state where the MOSFET becomes half on, and that could cause it to dissipate a lot of heat and fry. So what I did is I added another resistor here that just connects to 0 volts, and this is a 10K resistor. So if for some reason we have an undefined state over here, we will turn off the LEDs with this resistor. I don't know if this was a contributor for any reason, but if for some reason the GPIO was going crazy, this could potentially save us from that case. Now, my suspicion about why it failed before, the number one reason, and why it's working now, is because of this big chunky guy here that we added. When you have an inductive system, then that inductance, it has a lot of inertia, you could say, in the current that flows through. So normally with LEDs, that's not a problem. They behave almost like an ideal resistive load, you would say. But when you're powering a motor or anything with a coil in it, you usually need what's called a flyback diode, because when you have a lot of power going through, you can't just shut that power off. If you try to, you get a voltage spike because those pixies want to keep on going, and the MOSFET tells them they have to stop. They end up building up, and you get a really big voltage spike, and that voltage spike can go to 50 or 100 volts for a short period of time, and that can go through and fry the system. So I suspect that might have been what was happening before. If this goes to 100 volts, then that 100 volts goes through to the regulator on the Nano, then that's absolutely going to fry it, and I suspect that it did. So what this big chunky guy here is a diode. It's acting as a flyback diode, and ideally I would use like a high power Schottky diode or something like that for this case, because you want something that's going to turn on fast at just a little bit of a voltage rise, so that it quickly responds with a low dropout to handle a high current. But what this does is when you have the high energy flowing through all these LEDs, it gives it a path to continue going once this MOSFET turns off. So that's what this is for. Because I didn't have a good Schottky diode on hand, I used just another one of these MOSFETs. So when you're in a pinch, you can use a MOSFET as a diode, because just like it shows in this diagram here, the MOSFET has a little built-in body diode. So I just used that body diode. I tied the gate to the source so that it can't turn on, and now this is just there for its body diode, and it's using that good beefy body diode for the return current path for the flyback. And the reason why I put a heatsink on it is because this will potentially get our 14 amps for probably a short period of time, but during that time we want to make sure that we're keeping the package cool. I didn't know whether or not this would end up getting warm, but I have this many heat sinks available, and I figured out I could just take it off if I wanted to take it off later, which I might, because so far I have not found that this is warm to the touch when it's running. You can also see I added some capacitors, and the capacitors are right here. Just to give us a little bit of a shock absorber here. So when this gets shut off, there's some time that it takes for the diode to turn on, and before the diode turns on, instead of creating a really high voltage spike by having some capacitance here, it will charge the capacitor, which will kind of mellow out that voltage spike and give the diode more time to turn on before frying components. So I have the big electrolytic capacitors are there to give us a lot of bulk capacitance, and then I also have a few little baby ceramic capacitors in there. And those are there because they have a low equivalent series resistance, and they're really good at dealing with high speed, fast dynamics. So this will absorb the sharper part of the pulse, and this will absorb the bulkier part of the pulse. And then on the board, all I did is I changed the burnt out potentiometer to a new tension potentiometer. So those changes took this from a breaking system to a happy working system. And so far I've found that actually this doesn't get very warm when it's running. I expected it to be too hot to touch, and so I was planning on having it with a fan on the enclosure, but I'm not certain if I'm going to end up putting a fan on it. We'll see. I also want to show what I did for the software on the system. Now, I'm a big fan of Claude Code. It saves me a ton of time. It takes big work projects and turns them into simple little vibe coding projects, and it allows me to take a little hobby project 5 times farther than I probably would if I had to code it all myself. So I love vibe coding. So the way I approach this when I start a project is I start by writing a claude.md and a readme.md. The readme is for me. It tells me how the system works and things that I need to know, how to run it, how to build the code, just a high level stuff for people using the application. Then we have the claude.md, and these are instructions that I give to Claude AI. So in this case, in the Claude MD, I told it I want this project to be fast and simple. You're making me a platform.io program for my LED dimmer controller running an Arduino Nano. Read the README MD for goals and instructions. And then later I told it to use this hardware MD for hardware details. And I actually made it generate that for me after chatting a little bit and realizing that we should save the knowledge from that chat for myself and for the AI. So in the README, I wrote most of this README before I started telling Claude to build, and this is what sets up the application for success. You'll notice in the Claude, I told it I wanted to use platform.io. That's one bit, is you want to tell Claude how to work and what you're doing, and it's going to be easier for you to work with AI if you're using platform.io because there's no IDE that the AI has to go in and click and figure out how it works. Platform.io runs fully through the command line and with text files, and that's what AI is good at, and that's also what Git is good at. So before I wrote my first prompt to Claude, I set up the README, I set up claude.md, and what I also did is I went and I created this folder in the C drive. I made a folder code where I put my programming projects, and I put LED dimmer, and then I did shift right click open in terminal to open this location in a terminal, and I used the command git init to start a Git repository, and then when I had those files I did git add dot to kind of hit the save button, or prepare to hit the save button to make Git aware of my files, and then git commit -m initial commit. And this is like hitting the save, making a save file when you're playing a video game and you're about to go fight the final boss, and you want to make sure that if you screw it up, you have a save point that you can go back to. That's what this is. And Git works really well with text files. So trying to switch over to text-based code programs or build sequences is really, really helpful for working with Git and also for working with AI. So I did that. And then I basically just told Claude, hey, read the README and go. Ask me any questions you need to ask me, build a plan, and start writing. And it got really far on its first shot. It actually came up with a functional program that was workable. I think on the first shot, I can probably go back and check exactly what I had to say, and we might do that. But in the README, I give it the pins. I tell it the high level what we want to do with the program. I ended up saying, hey, we want a quick test to just put a 15% duty cycle on the Nano and see if it works. And that was the first thing that I got Claude to do, and we turned a little LED on and off on the benchtop was this LED. We put it to 15%. Then I got it to write the rest of the code, make it work with the dimmer switch and the presets. And then the code itself is in this main.cpp file, and you can just take a quick step through it. So we have our definitions for our classes, or not our classes, but our different functions, our different features. Then we have our state machine, button handling, more functions, and now here is the setup and loop that you're used to from Arduino. So in the setup, we initialize our PWM, set the registers for that, we set up our pins, how they need to be, and we start reading the potentiometer. Then in the loop, we check our potentiometer value. There's this delta function that helps us so that we can set a dead band. So little noise from the potentiometer doesn't trigger anything in the code. It waits for a certain delta before it takes action. Then here we have checks to look at where we're at in our state machine, if we're in analog mode or in preset mode. Because the way we have it working is when we click the button, it moves through different presets. We have preset 1 is a value of 6, preset 2 is a value of 100, and preset 3 is a value of PWM top, which I believe is 400. Yeah, 400. So the first time we click the button after powering up, it'll set the brightness to 6 out of 400. Then the next time we click it, it'll set it to 25% brightness. Then the next time we click it, it'll set it to 100% brightness. And the reason why these are so low, why our middle one is 25%, is because the human eye perceives brightness logarithmically. So what appears linear to the electronics, to our human eye, it looks like dark, bright, 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 and it looks like nothing is happening for most of the movement of your potentiometer knob, and then all of your brightness control happens in the very bottom little tiny bit. So that's the reason why the first preset is 6 out of 400, the next one is 100, which is 25%. 25% electrically looks like half brightness to the human eye, and this looks like just nice and dim TV watching mode when it's 6 out of 400. So that's one thing I really wanted Claude to do in the code, is to get this linearization of the knob so that moving the knob, what a human expects it to do is what it actually does. And the electronics have to deal with the weirdness of that logarithm. And the area of the code where that happens is right here. We set up a linearization lookup table. So here I set a floor value on the potentiometer. I say if it goes down to 800, then don't do anything. That just makes it so that if it goes all the way down, we have a nice cozy off mode, and it was more for the old potentiometer. It doesn't actually matter for this potentiometer. But here, as we walk up, we have these different steps where it's building a logarithmic curve or an inverse logarithmic curve out of these numbers. So I don't really want to take the time to explain it right now, but it's turning one straight line, which would work really poorly, into a bunch of straight lines that say on the low end make it so that I have to move the pot farther to get just a little bit of a change in brightness. Then as the brightness goes up, a change in the pot can make more of a change in the electrical brightness, until we get to the high end where a small change in the pot needs to make a big change in electrical brightness, so that what we expect from a turn of the knob becomes closer to what we see coming out of the lights, even though it's non-linear. This table lets us do that. So that's kind of at a high level how this works. And if I go and I type Claude/resume, then you can see in here I have two different Claude sessions that I used to make this program. So let's just go into the first one and let's take a look at kind of the history of this. So it looks like the first command I did, I just typed do the thing. I didn't have to explain anything because I already explained it all in the README document and in the CLOD, so it knew. It went and it read the README, it went and it read the CLOD. And it, on the first go, it created a platform.io environment and it created a main CPP. It actually skipped the basic implementation that I meant for it to do, and it went straight to a complete program. And that complete program ended up working. But as you can see here, it initially set the PWM to 62 kilohertz. And I knew from the math that I did before that 62 kilohertz risked making the MOSFET too hot and wasn't really valuable. I wanted 20 kilohertz because that way if it makes a little bit of noise, you can't hear it because the human ear can only hear up to 20 kilohertz. Most people can only hear probably up to 16, 17 kilohertz. So I wanted 20 kilohertz to make sure that it ran silently, but anything more than that, you end up getting more MOSFET switching losses. So I wasn't happy with 62.5 kilohertz, so I complained. I said, no, it'll get too hot, and I wanted it to fix it. Claude came back and it said, well, actually, we can't do that. If you're on pins 5 and 6, then that uses timer 0, and that's an 8-bit timer, so you have to choose between 62 kilohertz or 31 kilohertz, which I could have gone with 31 kilohertz, but I decided it was really easy to just switch to pins 9 and 10, so I did that. Then we could run at our 20 kilohertz because pins 9 and 10 use a different timer module. It's a 16-bit timer, and that gives us enough resolution to get actually exactly 20 kilohertz, which is exactly what I wanted. So that's what we did. I told it to make the change, and then it quickly just ran and made that change. Switched to timer 1, pins 9 and 10, 20 kilohertz. Great. Then I said build script because I didn't want to remember. I haven't used platform IO that much, so I just told it to make me a build script. And I like doing that anyway because then I can add things into the build script later if I want to. But it understood what I meant because this is a common request. So now I could run this to build it. Then something that I always do when I'm using Claude is I'm constantly getting it to update the README documents and the Markdown documents with a progress so that I can cancel out of a session and then start a new session with a fresh context, and it has all the information that it needs in the project file already without me needing to type more. And that's a really big part of how I do my vibe coding is I set up these Markdown documents in a way that Claude is going to be able to find the minimum amount of information that it needs to set its next job up for success. So put the usage of the build script in the README. That helps Claude and it helps me. So I can just quickly look in the README, see build. Oh, this is how I compile new changes and upload them to the board. Great. So it did that. Then I said I had to change the pinout for the button and the LED. Please change the code. So what I did is I went into the README. I had to change these. I'm not sure that I remember why. I think I wired up this pin header, and then I plugged it in, and I realized that I had it as black, blue, red. But in the code, I had it programmed as blue, black, red. So I just changed it in the program instead of resoldering. And I was like, Claude, do the thing, update the code, and it went and did that for me. I didn't have to go search, apparently we needed to change 3 places in the code in order to accommodate that. So I just made Claude do it because it did it faster and I could solder while it was doing that. Oh, apparently that was this change, so I honestly don't remember why I had to do this change. Oh, I do remember why. Actually, this one is because in the README I had it wrong at first. Then this one is what I just told you, switching A6 and A7. Okay, so I found that there was a minimum brightness, and even when we set PWM 0, the LED wasn't turning off all the way. So here you can see I'm asking Claude a question to help me troubleshoot. If I'm not 100% sure what it is, and I don't want to go and debug it all myself, I'll sometimes do this and kind of tell it what I'm thinking and ask what it's thinking. And sometimes it'll answer the question and find the reason before I can find the reason scanning myself. In this case, I'm really glad I did that because there was something I didn't know, which is that there is a quirk on AVR boards like the Arduino Nano with fast PWM mode, where PWM value of 0 doesn't actually produce 0 duty cycle, it produces 1 clock pulse every period. I didn't know that, but Claude knew that, and Claude already knew how to fix it. So it was a quick matter of going in and fixing it, and then turning down the knob all the way gave LED that was fully off. Great. Okay, next thing, I noticed that the pot wasn't quite going to its rails, so I wasn't getting quite the access to the full brightness range. So I made Claude generate a program so I could check and see how far it was going, and then ran that and put that information back into the program. And that was this pot reader and this pot calibration that we did, that you see described here. Is you can flash this pot reader program, sweep the pot around on 12 volts, and then you can go back and you can check and see what it is in the computer that you went to, and then you can put those changes in the code. And actually it made this nice function, so I could just send it through the, I didn't even realize it did that, but it looks like it created the ability to just use the serial console without even changing any code, just put it in the EEPROM, which is great. Okay, so here I was poking Claude's brain to see if it had any ideas on why it thought the big system burned out. So I think I had already finished everything, but I just wanted to poke its brain, see what it said. And I think actually at the time I had a capacitor sitting right here across the MOSFET. And I did a test on the little benchtop test LED, and I wasn't able to get that to dim. And I suspected it might have been because of this capacitor was keeping the charge and not letting it dim. And I didn't realize that that capacitor was actually a brain fart and would have been a really big problem if I plugged it in to the big power circuit, because on the big power circuit, the MOSFET would end up just charging and discharging that capacitor at full power, and it would have overheated the MOSFET and not really done much with the LEDs. So Claude helped me realize that that was a bad idea. I removed that MOSFET, everything worked great. Let's see. At this point, I asked it to create the hardware.md, which I never even looked at. I just wanted it here so that Claude could read it and know what was in the physical world. For me, I don't need this file. You know, I can look and see what the hardware is and what's plugged into what, but Claude doesn't know that. So by creating this hardware file, I gave the bot access to the information that it needed to understand the physical system. Okay, it flagged an issue. I didn't know at the time, but this A6 pin is analog input only. It can't do digital write. And I wired it up so that A6 actually is the 0-volt source for the pot. That's no good, and Claude flagged that for me, which is great. I don't think I would have realized that. So I just told it, yeah, I already fixed that. I already directly wired A6 to ground on the board. So I told it to update its memory and its files so it knew that. And that's it for the first Claude session. Then, in the second Claude session, I wanted to make it so that the minimum value of the potentiometer had a little bit of deadband, so I didn't lose out on brightness, because potentiometers are usually very non-linear at the bottom. So that was the first command, and here I'm just tweaking. Then I told it to rework the rest of the table, the linearization table with its best guess at linearizing for the human eye, and it did that, so I didn't have to play around and test as much. Because for me, normally I would fill this in manually, and I think I did tweak it manually on the bench before going over, but checking the wall and then coming back and programming and then checking the wall, it involves me plugging and unplugging everything over and over again, so I didn't want to do that too much, so I just got Claude to make a good guess. Okay, now at this point the old pot fully burned out. I was surprised. After the first failed test, it continued to work for a little while, but it did die finally, which is too bad because it has this nice click on the bottom that I like. But I had to now change the system to work nicely on the 10-turn pot. So I came up with an idea for how I wanted it to behave, so that I can do the full brightness sweep in 2 turns instead of 10 turns. And it kind of moves incrementally. It kind of notices where it is and then adjusts from where it is and goes brighter or darker as you move it around. So I just told it the shape of what I wanted it to do, and I made it make a plan for me that we could talk about. It asked me a question, I answered that question, then it updated its plan, and I liked what I saw, so I said go, and then it started writing in the changes to the program for me. Then I went and I tested it, and I noticed a bug, and the bug, I told Claude what the bug was, but basically when you plugged it into the wall, you would click the button and it would go to the bottom preset, and then it would just stay at the bottom preset and flicker. And I could use the potentiometer, and it would work okay-ish, but when I clicked the button, it would just turn off, and then clicking the button would go to the bottom preset again and turn off and go to the bottom, and it wasn't doing that thing where it cycles through low, medium, high, off. Low, medium, high, off is what it's supposed to do, and it wasn't doing that. The reason why it wasn't doing that is because of noise on the ADC on the potentiometer. So I told it that was probably the issue, but I had it just scan, look for another cause of the bug maybe. But Claude's like, no, yeah, that's exactly what it is. So it created this deadband with engagement. It made a separate deadband for switching from the preset mode to the analog mode, and it implemented that code. Okay, another issue is at low brightnesses, I noticed while testing it was jumping too much. And you can still actually see that it jumps between digital values as it goes up. And that's because the software, the PWM is, I think, well, it's only 400 values. So value 1 and value 2 and value 3 were too big of a jump to the human eye, and I didn't like that. So I suggested one solution to it, and it said, yeah, that will work, but I think we should do this other solution instead called temporal dithering. And that switches the PWM between 0 and 1, or between 1 and 2, or between 2 and 3, and it creates a few pseudo values between. And I liked that solution, so I told it to go ahead and make the dithering code changes, so it implemented that. And it's interesting, it did all these things in a different way than I would have done it, but it works, and it works nicely, and it's so much faster, and I can get it to take care of its own garbage. So I really, really enjoy that, even though it's maybe not exactly how I would have written it. And, you know, theoretically, there are some advantages to what I had in my head, but pragmatically, you can't really tell the difference in any way that actually matters. So it's better. Okay, here I kind of had two things in one. I wanted to make sure that dithering went all the way up to maximum brightness, not just at the low end. But I also wanted to implement oversampling, because in testing, if the ADC was kind of between two values, if the potentiometer was kind of between two bins for the computer to recognize, then it was unable to, well, the computer would flicker back and forth between what it thought the potentiometer should be on. And that meant that the LEDs would flicker in brightness between two values because they're trying to follow the knob. So the way that I wanted to solve that is with a technique called oversampling, where you don't just read the potentiometer once, you actually read it, in this case, 16 times, and you take the average of those 16 readings, and instead of count from 0 to 1024, it increases to, I thought it was doing 16 counts. It is doing 16 counts. But it ended up switching it to from a 0 to 1024 up to a 0 to 4092 scale. So that made it much less jittery. Now there's not really any flicker on the lights. So that was the plan that it made, and I said do it, and it went and did it. And then I was pretty happy with how it behaved. I checked the context to see how much I was using, and generally want the context to be pretty low. I actually let this go higher than I would normally like. And I ended the conversation there, and that's the code that's running now, actually. Although I think I manually adjusted the preset values, because originally the preset values were at like 30 and 200 or something. Maybe it was even 60 and 200, and I wanted a way lower dim setting, so I dropped that down to 6, and I kind of like 6, and 100 instead of 200 for the medium. And that's it. So I hope that gives some insight on how you can vibe code a simple Arduino project with Claude Code, and it's such a nice tool. It costs about $30 a month, but I haven't had a month go by where I haven't gotten the full value out of that since I started the subscription. And I learn so many more tools because I can just say, hey Claude, do it using this toolkit. And instead of having to go and read all these documents to figure out how to get started on my project, Claude can usually just kind of build it and do that annoying initial research part for me. Then the example that I'm reading is my own project that Claude already started for me. So it's an excellent learning tool as well. But anyway, if you have any other questions, post comments. And either me or someone else will probably give you a reasonable answer about it. And if you have other ideas about how to use the code, drop a comment. I love reading other people's ideas. And if you think this or that was dumb or whatever, let me know, and I'd love to see it.